telescope 1 million miles from Earth is staring into the past and finding things that should not be there. Galaxies fully formed when the universe was barely 100 million years old. Structures so massive they break the laws we built cosmology on. A signal from deep space firing every 16 days on a perfect schedule, with no confirmed source. We are going to travel through all of it. Dark matter you can see colliding. A bruise that might be a scar from another universe. A black hole at our galaxy's core that woke up and scarred everything around it. If you enjoy the journey, like and subscribe. It genuinely helps. Now hold on, we begin. 1 million miles from Earth, a machine the size of a tennis court is rewriting history. The James Webb Space Telescope, launched in December of 2021. Scientists had spent 30 years and $10 billion building it. The goal was straightforward: look further back in time than any instrument ever had, and fill in the gaps of our cosmic story. What they found instead cracked that story open. Within months of its first images, Webb detected galaxies that were fully mature, fully structured, and burning with hundreds of billions of stars. That alone sounds impressive. The problem is, when they existed, these galaxies were observed as they appeared just a few 100 million years after the Big Bang. And that timeline breaks everything. Here is why. After the Big Bang, the universe was a hot, dense fog of particles. Gravity had to slowly pull hydrogen gas together into clumps. Those clumps had to collapse into the first stars. Those stars had to live, die, and explode, seeding space with heavier elements. Then new generations of stars had to form around those materials. Then gravity had to gather millions or billions of stars into a galaxy. That entire process, by every model physicists had built, takes billions of years. Webb found galaxies that skipped the line. One galaxy in particular, spotted in early 2023, appeared so massive and so structured that a team of scientists calculated it should have taken the entire current age of the universe to build. Yet there it was, fully assembled, when the universe was less than 1% of its current age. One researcher described it openly as an universe breaker. That phrase, coming from a peer-reviewed paper, says everything. To picture this, imagine arriving at a construction site at 7 in the morning and finding a 40-story skyscraper already standing, fully furnished, with people living inside. You have a time-lapse showing the concrete was poured at 6:55. 5 minutes of construction for a 40-story building. That is the scale of impossibility Webb dropped on cosmology. Scientists immediately started working through explanations. Some proposed that the early universe formed stars far more efficiently than models predicted, perhaps converting gas into stars at nearly 100% efficiency compared to the few percent our current models allow. Others suggested that dark matter, the invisible substance making up most of the universe's mass, may clump and behave differently in the early universe than anyone assumed. A smaller group raised a more uncomfortable idea, that our model of cosmic history has a gap we have never noticed before, because we never had a telescope powerful enough to see this far back. None of these explanations are confirmed. All of them are actively being tested. What is confirmed is the observation itself. The galaxies are real, the timestamps are real, and the gap between what we expected and what we found is real. Webb is still observing. Every new data release adds more candidates to the list of galaxies that should not exist yet. The count is growing. What makes this more than an abstract puzzle is what it implies for everything built on top of the standard model of cosmology. Estimates of the universe's age, predictions for how structure forms, theories about where we sit in the timeline of cosmic history, all of them carry an assumption that we understand how the early universe worked. Webb is testing that assumption directly, and right now, the assumption is bending. The galaxies Webb found had to come from somewhere. They needed raw material. They needed a process fast enough to build them in almost no time. And that process starts with something we have never actually seen. The very first stars. The first stars ever born looked nothing like the Sun. Before a single galaxy existed, before any planet, before any element heavier than hydrogen had ever been made, the universe was a cold and featureless dark. Gravity pulled the lightest gas in existence into slowly tightening knots, and then, roughly 100 to 200 million years after the Big Bang, the first stars switched on. Scientists call them population 3 stars. They are confirmed to have existed through indirect evidence, but no one has directly observed a single one. Every population 3 star burned out long before any telescope existed. What we know about them comes from theory, from the elements they left behind, and from the mathematical fingerprints they pressed into the next generation of stars that followed. And what theory tells us is extraordinary. Population 3 stars were monsters, with nothing but pure hydrogen and a tiny trace of helium to work with. They had to grow enormous to generate enough pressure in their cores to fuse anything at all. The smallest estimates put them at several times the mass of our Sun. The largest theoretical models suggest some of them may have been 10,000 times more massive. A star that size burns so hot it glows blue-white and fires radiation in every direction with a ferocity that modern stars cannot match. Picture our Sun as a campfire. Population 3 stars were industrial furnaces the size of cities. The energy output was almost violent. They also lived and died fast. Massive stars burn through their fuel at a punishing rate. Where our Sun will last roughly 10 billion years, a population 3 star may have lasted only a few million, some possibly less. They ignited, tore through their hydrogen, and then collapsed or exploded in a supernova so powerful it seeded the surrounding gas cloud with the first heavy elements the universe had ever produced: carbon, oxygen, iron, silicon. Every atom heavier than helium in your body was forged in a star like this. Webb has been hunting for direct evidence of population 3 stars since its first observing run. In 2023, a research team announced a candidate, a galaxy observed at extreme distance, showing a chemical signature consistent with population 3 stellar activity. The detection is labeled a strong candidate, not a confirmed sighting. Verification requires more observation, but the community treated it as a breakthrough because the signature matched the theoretical predictions almost precisely. Here is what makes this search urgent beyond scientific curiosity. The population 3 stars did not just produce elements. They ended the cosmic dark ages. Their ultraviolet radiation ionized the surrounding hydrogen gas, punching holes in the fog that had kept the early universe opaque. This process, called reionization, is what allowed light to travel freely through space for the first time. Without it, the universe stays dark and formless. With it, the stage is set for everything that follows, including galaxies, planets, and eventually life. So when Webb found those impossibly old, impossibly large galaxies in Chapter 1, the population 3 stars are the engine behind the question. If the first galaxies assembled faster than expected, then either the population 3 stars were more efficient than modeled, or there were more of them, or they behaved in ways the current theory does not account for. Every answer leads to the same deeper problem. Something in the early universe was moving faster than the physics we know should allow. And when scientists started looking at the scaffolding holding all that structure together, what they found beneath the galaxies was even harder to explain. Pull back far enough from any galaxy, and you stop seeing stars. You start seeing something else entirely. Spread across the observable universe is a structure so vast that individual galaxies are just specks of light clinging to its surface. Scientists call it the cosmic web. It is a confirmed feature of our universe, mapped by multiple independent surveys over decades, and it looks exactly like what its name suggests: a three-dimensional web of filaments, sheets, and knots, stretching across distances so large that the human mind genuinely struggles to process them. The filaments are made of gas, dust, and dark matter, threaded together by gravity over billions of years. Where filaments intersect, matter piles up into the densest regions in the universe. Those intersections are where the largest galaxy clusters sit. Between the filaments, separated by the structures like the gaps between threads, are enormous empty bubbles called voids. We will return to those later. For now, the web itself demands attention. A single filament connecting two galaxy clusters can stretch for hundreds of millions of light years. The largest known filaments extend for over 1 billion light years. 1 billion light years of connected structure, continuous, threaded with matter, sitting in the dark. The web was predicted theoretically before it was observed. In the 1980s, simulations of how matter should clump under gravity produced a web-like pattern almost automatically. When real surveys started mapping galaxy positions in 3 dimensions, the web appeared exactly as predicted. That match between theory and observation is one of cosmology's great successes. Here is where it gets complicated. The web forms because of gravity. Gravity pulls matter towards denser regions, which become denser still, which pull more matter, which build filaments, which guide galaxies to cluster intersections. Simple enough in principle, difficult in practice, because the math only works if most of the mass doing the pulling is invisible. Ordinary matter, the kind that makes up stars, planets, and everything you can touch, accounts for only about 5% of the universe's total mass and energy. Dark matter accounts for roughly 27%. Without dark matter, the simulations produce a universe that looks almost nothing like what we observe. With it, the cosmic web emerges naturally. So the web is, in a very direct sense, a map of dark matter. The filaments trace where dark matter flows. The knots mark where it concentrates. The voids mark where it is absent. But in 2020, a team of astronomers made an observation that added a new layer of strangeness to the web. They detected filaments rotating, entire structures hundreds of millions of light years long, slowly spinning as a coherent unit. Filaments at this scale were expected to grow and stretch, pulled outward by the expansion of space. Spinning as a single structure was unexpected. The rotation implies that something during the web's formation imprinted angular momentum across distances that should not be able to coordinate that kind of motion. Scientists are working through explanations. Some point to conditions in the very early universe, before the web fully formed. Others suggest the explanation will require understanding the large-scale behavior of dark matter in a new way. The cosmic web connects everything, and something is making parts of it spin. Stranger still, hidden inside the web structure, is a signal that may be the first glimpse of dark matter doing something it was never supposed to do. In 2014, astronomers scanning X-ray data from galaxy clusters noticed something that had no business being there. A faint line of X-ray emission, sitting at an energy level of 3.5 kilo-electron-volts, appeared in the data. X-ray emission lines are common in space. Hot gas glows in X-rays, and the specific energy of the glow tells you which element produced it. Every known element and ion that could plausibly be present in a galaxy cluster had already been catalogued. Every known line was accounted for. The 3.5 kilo-electron-volt line matched none of them. The detection came from 2 independent teams analyzing separate datasets. One group examined data from dozens of galaxy clusters stacked together. The other examined the Perseus cluster and the Andromeda galaxy separately. Both found the same unidentified line. The overlap was treated as significant. A signal appearing in independent datasets at the same energy level is hard to explain away as instrument error. The leading candidate explanation: dark matter decay. One theoretical class of dark matter particles, called sterile neutrinos, is predicted to very occasionally decay. When a sterile neutrino decays, it releases a lighter neutrino and a photon at a specific energy. The math predicted that decay photon would appear at roughly 3.5 kilo electron volts. The signal matched the prediction almost exactly. Confirmed? No. A strong candidate? Yes. The scientific community has been debating it for over a decade. In the years since, follow-up observations produced contradictory results. Some pointed telescopes at regions expected to show the line and found it. Others found nothing. The James Webb Space Telescope is now capable of contributing to this search in new ways. Results are ongoing. Here is why this matters beyond the physics. Dark matter has never been directly detected by any instrument. Every piece of evidence for its existence is gravitational. We see what it pulls. We measure where it bends light. We watch how it shapes the cosmic web. Every single one of those detections is an inference. The 3.5 kilo electron volt line, if confirmed, would be the first time dark matter left a direct photon signature, the first time it actually produced light a detector could catch. That would change the entire strategy for studying the universe's invisible majority. Right now, dark matter detection experiments are underground laboratories waiting for a particle to bounce off an atomic nucleus. A photon signal in X-ray data means space telescopes become dark matter detectors. The toolkit expands overnight. Even if the sterile neutrino interpretation turns out to be wrong, something produced that line, and no one has fully explained what. To understand just how extraordinary a direct detection would be, consider how completely dark matter dominates the universe's structure. Ordinary matter, the atoms, stars, planets, gas clouds, all of it is a minority, a small fraction of the total. The dominant material is invisible, and we have built our entire picture of cosmic history around something we have never touched. But there is one place where we have actually seen dark matter and normal matter physically separated from each other, with our own instruments, in a collision so violent it pulled them apart. About 3 billion light-years away, two galaxy clusters slammed into each other at millions of miles per hour. The collision happened long before any human existed. By the time the light reached us and a telescope caught it, the event had already played out. What we observed was the aftermath, a system called the Bullet Cluster, one of the most studied objects in modern astronomy, and the clearest visual proof that dark matter is real and physically distinct from everything else. Here is what happens when galaxy clusters collide. The clusters themselves are mostly empty space. Individual galaxies within each cluster pass through each other almost without interaction, because the distances between stars are enormous. The galaxies themselves survive largely intact. What does collide is the hot gas that fills the space between galaxies in each cluster. That gas, called the intra-cluster medium, carries most of the ordinary matter in a cluster. When two clusters crash, the gas clouds slam together, heat up to millions of degrees, and slow down dramatically from the shock. You end up with a hot, glowing cloud of gas sitting roughly in the middle of where the two clusters met. Now here is the key observation. To find where the mass is, astronomers use gravitational lensing. Massive objects bend light passing near them, and by measuring how much the light from background galaxies is distorted, you can map the mass distribution of whatever is doing the bending. When scientists applied this to the Bullet Cluster, the mass was nowhere near the hot gas. The mass, two large concentrations of it, was far out on the sides, moving outward, continuing forward, as if the collision had barely slowed it down. The ordinary matter, the gas, stopped in the middle. The majority of the mass kept going. Something massive passed through the collision, almost without interacting. That something is dark matter. Dark matter does not interact with normal matter through electromagnetic force. It does not slow down from pressure or friction. It barely interacts with anything except gravity. So when the two clusters collided, the dark matter from each cluster passed straight through the other, like two ghosts walking through the same wall. The gas stopped. The dark matter continued. The bullet cluster observation is confirmed. Multiple analyses using different techniques reach the same conclusion. Some scientists had theorized that the gravitational effects attributed to dark matter could be explained by modifying the laws of gravity instead. The bullet cluster makes that explanation nearly impossible to sustain because you can see the mass and the matter separately in different locations at the same time. A teaspoon of the hot gas in the bullet cluster weighs more than a car. The entire gas cloud holds enough ordinary matter to make the observations dramatic. And still, the dark matter outweighs it by a factor of roughly 5 to 1. The bullet cluster is a collision that took billions of years to happen and reached us as one of the most important images in the history of physics. It confirmed the invisible. It separated it from everything else. And it closed one of the biggest escape routes from accepting that most of the universe is made of something we still cannot identify. So we know dark matter is real. We know it outweighs normal matter by a huge margin. What we still cannot explain is what it is made of, where it came from, or how it behaves on the smallest scales. And if dark matter is the great mystery of what the universe is made of, what comes next is the great mystery of where the universe is going. In 1998, two separate teams of astronomers were racing to measure how fast the universe's expansion was slowing down. They expected to measure a slowdown. Gravity pulls matter together. The Big Bang threw everything outward. Logic said gravity should be winning over time, gradually applying the brakes. The question was simply how hard. Both teams used exploding stars called Type 1a supernovae as measuring tools. These explosions are remarkably consistent in brightness, making them reliable distance markers across cosmic scales. Both teams found the same result. The expansion was not slowing down. It was speeding up. The universe is not coasting. It is accelerating. Something is pushing space itself outward faster and faster, and the source of that push is unknown. Scientists named it dark energy, and 3 researchers won the Nobel Prize in Physics in 2011 for the discovery. The name sounds like something from a science fiction script. The reality is more unsettling. Dark energy is a label for a phenomenon science can measure, but cannot explain. Here is how dominant dark energy is. Of all the mass and energy in the universe, ordinary matter accounts for roughly 5%. Dark matter accounts for roughly 27%. Dark energy accounts for approximately 68%. The majority of everything is a force we cannot identify, doing something we cannot explain, at an accelerating rate we cannot predict far into the future. The simplest mathematical description of dark energy treats it as a property of space itself. Empty space has a baseline energy level, a kind of pressure built into the fabric of the universe. As the universe expands and creates more space, more of this energy appears, pushing expansion faster. This idea, called the cosmological constant, fits the current data reasonably well. But fitting the data and explaining the physics are different things. No one knows why empty space should have energy. The theoretical value physicists calculate from quantum mechanics. For the energy of empty space is somewhere around 10 to the power 120 times larger than what we actually observe. That discrepancy between prediction and measurement is the largest in all of physics. Some scientists propose that dark energy is a dynamic field that changes over time, called quintessence. If true, the expansion rate of the universe has not been constant throughout history and will not be constant in the future. Results from the Dark Energy Spectroscopic Instrument, published in 2024, showed tentative hints that dark energy may be evolving. The data is preliminary. It requires confirmation. But if it holds, it means the cosmological constant is wrong, and the universe's future is even less predictable than current models suggest. For humanity, the implications extend beyond philosophy. A universe with accelerating expansion means galaxies are slowly moving beyond the reach of each other. The further they drift, the more the light from distant galaxies redshifts past detection. Far enough in the future, perhaps trillions of years from now, the observable universe shrinks to just our local group of galaxies. The rest of the cosmos disappears past a horizon permanently unreachable. The acceleration is already happening. At current rates, the most distant galaxies visible to Webb today will eventually vanish from any future telescope's view. Dark energy is pulling the universe's future into a shape we are only beginning to recognize. And that future depends entirely on a number that two separate measurement methods refuse to agree on. The universe has a speed, a rate at which space itself is expanding, measured in miles per second per megaparsec, named the Hubble constant, after the astronomer who first measured it. Knowing this number precisely means knowing the universe's age, its size, and its future with confidence. Scientists have been refining this measurement for nearly a century. There are two primary methods for measuring it. Both are rigorous, both are supported by decades of data, both are verified by independent teams, and they produce different answers. The first method looks at the early universe. The cosmic microwave background is the faint glow of radiation left over from 380,000 years after the Big Bang, the moment when the universe first became transparent and light could travel freely. Its pattern encodes the precise conditions of the early universe. The Planck satellite mapped this radiation in extraordinary detail. Using that map and the standard model of cosmology, scientists calculated the Hubble constant at around 67 kilometers per second per megaparsec. The second method looks at the nearby universe. Astronomers measured distances to galaxies using a ladder of overlapping techniques. Pulsating stars called Cepheid variables calibrated against supernovae, each rung checked against the last. This approach consistently produces a value of around 73 kilometers per second per megaparsec, 67 versus 73. The gap sounds small. In cosmology, it is enormous. When the discrepancy first appeared, many assumed it was measurement error that would resolve itself as instruments improved. Webb was partly launched to settle it. Instead, Webb sharpened both measurements and the gap remained. The precision of each method increased, which means the gap between them is statistically significant and growing harder to dismiss as accident. Scientists call this the Hubble Tension. Tension is the polite word. What it actually represents is a potential crack in the foundation of cosmology. Both measurements cannot be simultaneously correct. Either one of them has a systematic error that no one has identified despite decades of checks, or the standard model of cosmology is missing something fundamental that affects how the universe expanded at different points in its history. Some proposed solutions involve new particles that were active in the early universe and then faded. Others suggest dark energy behaved differently in the past. One model proposes a brief burst of a separate energy field, sometimes called early dark energy, that slightly sped up expansion just before the cosmic microwave background was released, which would explain the gap between the two measurements. None of these solutions are confirmed. All are active research areas. What is confirmed is that the Hubble tension is real. After multiple independent checks with multiple telescopes using multiple techniques, the two numbers persist. They do not converge, and every year of additional data makes a simple error explanation less likely. Two measuring systems, both designed to describe the same universe, refusing to agree. And when you start questioning the expansion rate, a deeper question surfaces. If we cannot fully agree on how fast the universe expands, are we even sure we know what shape it has? Every map of the universe assumes the same thing: that space is flat. Flat in the geometric sense. Parallel lines stay parallel forever. Triangles have angles that add up to 180 degrees. The universe extends outward in all directions without curving back on itself. This assumption is baked into every cosmological calculation, every simulation of large-scale structure, and every projection about the universe's future. A research team in 2019 published an analysis of Planck satellite data and concluded the assumption might be wrong. Their analysis suggested the cosmic microwave background data is more consistent with a positively curved universe, meaning a universe shaped roughly like the surface of a sphere, extended into dimensions we cannot visualize. In a positively curved universe, parallel lines eventually converge. Triangles have angles adding up to more than 180 degrees, and if you traveled far enough in one direction, you would eventually return to where you started. The paper caused immediate controversy. Other researchers argued the team's statistical method was flawed, that the same data could support a flat universe with equal validity depending on how the analysis was framed. The debate is ongoing and unresolved. Here is why the question matters beyond geometry. In a flat universe, the cosmological calculations physicists use for everything from galaxy formation to dark energy behavior are calibrated correctly. In a positively curved universe, those same calculations require adjustment. The corrected versions produce a different Hubble constant value, specifically a value closer to the cosmic microwave background measurement, which could resolve the Hubble tension. If the universe is curved, the tension may vanish. Two problems solved by one geometric correction. However, the evidence for flatness is strong. Multiple measurements across multiple instruments have consistently found the universe's curvature to be indistinguishably close to zero. The 2019 paper sits against that consensus. Its authors stand by the analysis. Mainstream cosmology has not adopted the finding, but it has also struggled to fully dismiss it. To picture what a curved universe means at the observable scale, the sphere analogy breaks down for the three-dimensional case. But consider how no matter where you stand on Earth's surface, you see a horizon in every direction. The surface curves away from you everywhere equally. A positively curved universe would behave similarly for any observer, with the curve happening across all three spatial dimensions simultaneously and across distances many billions of light years beyond anything we can see. Our observable universe would be a small patch on the surface of something far larger, curving away in all directions past the limits of detection. And somewhere in that invisible region beyond our horizon, there may be features so unusual they have left their marks on the sky we can see. One mark in particular has been staring at astronomers for decades. A cold, empty patch in the microwave background too large to explain, sitting in the southern sky, 1 billion light-years wide. Something is wrong with a patch of the sky the size of roughly 1 billion light-years across. The cosmic microwave background radiation covers the entire sky. It is an almost perfectly uniform glow, the fossilized light of the early universe pressed into every direction. Tiny fluctuations in temperature across its surface gave rise to all the structure we see today: galaxies, clusters, the cosmic web itself. Those fluctuations are small and mostly random, scattered across the sky without obvious pattern. Except for one spot in the southern sky, first clearly identified by astronomers in 2004. This region is measurably colder than the surrounding background. The temperature difference is tiny in absolute terms, but statistically enormous. When the distribution of temperature fluctuations across the full sky is analyzed, a cold patch of this size and this depth should appear by chance less than 2% of the time. Some analyses put the probability even lower. The cold spot, as it is now formally called, is real, confirmed by multiple instruments, including the Planck satellite, and it remains unexplained. The leading ordinary explanation involves a supervoid. A supervoid is a region of space with significantly less matter than average. As cosmic microwave background photons travel through a supervoid, they lose a small amount of energy due to the expanding space inside the void. If the supervoid is large enough, the effect accumulates and imprints a cold signature on the background radiation. Astronomers identified a large underdense region in the approximate direction of the cold spot, located roughly 3 billion light-years away. The problem is size and depth. Studies of this supervoid have consistently found it large enough and empty enough to explain some of the cold spot's signature, but the calculations fall short. The supervoid accounts for perhaps 20% of the observed temperature anomaly. The remaining 80% has no ordinary explanation. This is where the more radical idea enters. Some cosmologists have proposed that the cold spot is a bruise. When two soap bubbles collide, the contact point shows a ring of disruption where the surfaces met. In certain theoretical frameworks where multiple universes exist as separate regions of space, each one a bubble, a collision between our universe and a neighboring bubble would create an imprint in our cosmic microwave background. The imprint would be cold, roughly circular, and too extreme to explain by structure within our universe alone. Confirmed? No. A testable prediction? Partially. Astronomers have proposed specific signatures that bubble collision models predict, a specific pattern of temperature and polarization at the cold spot's edge, distinct from what ordinary processes would produce. Planck data has been analyzed for these signatures with inconclusive results. The James Webb Space Telescope and future instruments may add new measurements. The supervoid explanation is the consensus candidate. The bubble collision explanation is speculative but scientifically serious enough to appear in peer-reviewed literature and generate testable predictions. 1 billion light-years wide, confirmed anomalous, partially explained by a structure that accounts for a fraction of what is observed, and the remainder of the signal pointing towards something outside our universe. If the bubble collision idea is correct, it means the multiverse did something to us physically. It left a scar on our sky. And the multiverse itself, which most people associate with science fiction, is a consequence of ideas that come from real physics. The word multiverse tends to arrive in conversations about superhero films and alternate histories. The scientific version of the idea is colder, stranger, and arrived as an unwanted consequence of physics that already works. The multiverse concept in cosmology comes primarily from a theory called eternal inflation. Inflation itself is confirmed in its basic form. The universe underwent a period of extraordinary rapid expansion in the first fraction of a second after the Big Bang, stretching space by an enormous factor almost instantly. The evidence for this is strong. The uniformity of the cosmic microwave background, the flatness of space, and the pattern of temperature fluctuations all match inflationary predictions with high precision. Eternal inflation is the theoretical extension of this idea. In the eternal inflation framework, inflation never fully stops everywhere at once. Instead, it keeps going in most of space, while occasional regions stop inflating and settle into stable conditions, like our universe. Each region that stops becomes what theorists call a bubble universe, a self-contained cosmos with its own properties, its own physics potentially, expanding inside an ever-inflating background that continues producing new bubbles without end. If eternal inflation is correct, and the majority of cosmologists working in this area believe the basic inflationary mechanism is sound, then the multiverse is a structural consequence. Separate bubble universes exist whether we like the idea or not. They are not accessible because the space between bubbles inflates faster than light can cross it. They are separated from us by a horizon that cannot be crossed, except, possibly, by a collision. In the very early moments of any bubble universe, when inflation first ends and the bubble is still microscopic, it could theoretically collide with an adjacent bubble before they are fully separated. That collision would leave a mark, a distortion in the early universe that stretches to cosmic scales as expansion continues. The cold spot is the candidate for exactly that mark in our sky. Other physicists push back on eternal inflation and the multiverse on scientific grounds, a theory that predicts everything because it contains infinite universes with all possible properties becomes very hard to test. If every outcome is possible somewhere, the framework risks being untestable as a whole, which some argue disqualifies it from being science in the strict sense. The debate is genuine, serious, and ongoing in the physics community. One scientist who found eternal inflation too convenient proposed something even more radical. His model does not require other universes existing now, parallel and unreachable. His model says the universe before ours died, and what we call the Big Bang was its funeral. Roger Penrose is one of the most respected mathematical physicists alive. He shared the Nobel Prize in 2020 for his work proving that black holes are a direct consequence of Einstein's equations. When he proposes a model of the cosmos, the physics community listens, even when the model is deeply unconventional. His theory is called conformal cyclic cosmology. The core claim is that our Big Bang was not the beginning of time. It was the transition point between a previous universe and ours. And before that, another transition. And another. The universe cycles through an infinite series of eons, each one beginning in a Big Bang that is the collapsed endpoint of the one before it. The mechanism Penrose describes rests on one central observation. At the very end of a universe, after all stars have burned out, all protons have decayed, and all black holes have evaporated through a process called Hawking radiation. The only things left are massless particles like photons. Massless particles do not experience time in the conventional sense. They also have no intrinsic scale. A massless particle cannot carry information that distinguishes large from small. The dying universe, Penrose argues, eventually loses all information about size. It becomes scale-free, and a scale-free dying universe is mathematically indistinguishable from the scale-free conditions at the beginning of a new Big Bang. The end and the beginning look identical in the equations. The transition is smooth. The theory makes a specific prediction. Events in the dying universe, specifically the last mergers of supermassive black holes just before they finally evaporate, should leave patterns in the cosmic microwave background of the next universe. These patterns, called Hawking points, would appear as faint concentric rings of slightly different temperature, the echo of a black hole's final evaporation pressing through the transition. A team searching for these rings in Planck satellite data announced in 2020 that they found statistical evidence for anomalous circular patterns consistent with the Hawking point prediction. Penrose considered it supportive. Independent analyses disputed the methodology. The debate continues. Confirmed? No. Testable? Yes, with current and future instruments. The theory is scientifically productive, meaning it generates predictions that can be checked against real data, which separates it from pure speculation. What conformal cyclic cosmology adds to the picture is a profound shift in how to think about the Big Bang. Every other cosmological model treats the Big Bang as a starting condition, a boundary beyond which physics cannot reach. Penrose's model dissolves that boundary. The Big Bang becomes a moment in a longer story, not the first page. Our universe, on this picture, inherited something from the one before it. The echoes are waiting to be confirmed. While physicists wrestle with the universe's origins and its cycles, the sky above us is broadcasting signals from the opposite end of the energy spectrum. Short, violent, arriving from billions of light years away. And most of them have no confirmed explanation. On April 28, 2020, a signal reached Earth that lasted less than a second. It was a fast radio burst, a pulse of radio waves concentrated into a fraction of a millisecond, carrying more energy than the sun releases in several days, arriving from an extreme distance with no visible source. Fast radio bursts had been detected before, hundreds of them since the first confirmed detection in 2007. What made this one extraordinary is where it came from. Our own galaxy. Every fast radio burst detected before this one had arrived from millions or billions of light years away, distances so extreme that identifying the source was essentially impossible. This burst, designated SGR 1935 + 2145, came from a magnetar inside the Milky Way, only about 30,000 light years from Earth. For the first time, astronomers had a fast radio burst with a confirmed source they could actually study. The source magnetar is one of the most extreme objects in the known universe. A magnetar is a dead star, specifically the collapsed core of a massive star after it exploded as a supernova. It packs roughly 1.5 times the mass of our entire sun into a sphere roughly 12 miles across. Its magnetic field is 1,000 times stronger than a standard neutron star and roughly 1 quadrillion times stronger than Earth's magnetic field. To grasp what that means physically, the magnetar's magnetic field would rip the iron from your blood before you got within 1,000 miles of it. At the surface, it would tear apart individual atoms, separating electrons from nuclei by brute magnetic force. The material at a magnetar's surface is not in any state that exists anywhere else in the observable universe. The confirmed detection of a fast radio burst from a magnetar answered one question. At least some fast radio bursts come from magnetar activity. The exact mechanism is still under investigation. One leading model involves starquakes on the magnetar's surface, where the crust fractures and releases enormous amounts of magnetic energy in an instant. Another involves interactions between the magnetar's magnetic field lines snapping and reconnecting, similar to solar flares but incomprehensibly more powerful. What the 2020 detection did not answer is whether all fast radio bursts come from magnetars. Some bursts repeat on irregular schedules. Some repeat on suspiciously regular schedules. One source repeats every 16 days with clockwork precision. A physical process on or around a single magnetar should not produce a 16-day cycle with that consistency. The regularity implies a larger system, an orbital period, a companion object, or a geometric factor that opens and closes a line of sight on a fixed schedule. None of those explanations are confirmed. The 16-day repeater remains one of the genuinely open mysteries in observational astronomy. And if magnetars can produce fast radio bursts by sheer force of magnetic energy, the question becomes just how much power a magnetar can actually generate. The answer goes well beyond radio waves. A magnetar sits quietly for years, decades, sometimes centuries. And then, without warning, it cracks. When a magnetar starquakes, the energy released in a fraction of a second can briefly outshine the combined light output of every star in our galaxy. Not invisible light. In gamma rays and X-rays, the most energetic forms of radiation that exist. A magnetar flare arriving from the far side of our galaxy can saturate satellite detectors and briefly ionize Earth's upper atmosphere, despite the distance of tens of thousands of light years. This is confirmed on December 27, 2004. A flare from a magnetar designated SGR 180620 reached Earth and caused measurable ionization effects in the ionosphere. The magnetar sits roughly 50,000 light-years away. The flash was bright enough that instruments originally designed to study gamma-ray bursts from distant galaxies went temporarily blind from the brightness of something inside our own. Magnetars are born in supernova explosions, when a massive star, roughly 10 to 25 times the mass of our Sun, exhausts its nuclear fuel and collapses. The core implodes in milliseconds. The collapse compresses the core to nuclear density, packs more mass than the Sun into 12 miles, and spins it up to extraordinary rotation speeds through conservation of angular momentum. Most collapsed cores become regular neutron stars. A magnetar forms when conditions during the collapse generate a particularly powerful dynamo effect, amplifying the magnetic field to levels that dwarf anything else in the universe. Neutron stars themselves are already extraordinary objects. The density inside a neutron star is so extreme that normal atomic structure ceases to exist. Electrons are forced into protons, producing neutrons packed against each other at nuclear densities. A single teaspoon of neutron star material carried to Earth would weigh roughly 1 billion tons. The surface gravity is 100 billion times Earth's. A human standing on the surface, if such a thing were somehow possible, would be instantly flattened to a layer a few atoms thick by tidal forces alone. Magnetars push past even those extremes. The magnetic field energy stored inside a magnetar is so large that it contributes noticeably to the object's mass. The field physically distorts the star's shape. The crust, a layer of crystallized nuclear material roughly a mile thick, is under constant stress from the competing forces of magnetic energy trying to shift the field geometry, and the enormous gravity trying to hold everything in a sphere. When the stress exceeds what the crystallized crust can bear, the crust fractures. That fracture is the starquake. The magnetic field snaps to a new configuration. The energy released is the flare. The speed of this process is staggering. A magnetar starquake releases the equivalent of years of the Sun's total output in roughly 1/10 of a second. The radiation front travels outward at the speed of light. Objects between the magnetar and Earth, gas clouds, dust, other stars, have no warning and no protection. Within our galaxy, the nearest known magnetar is roughly 9,000 light-years away, comfortably distant. But 9,000 light-years is not the universe. And when scientists began finding neutron stars with masses approaching the absolute boundary that the equations of physics allow before collapse into a black hole, the question of what sits at that edge became urgent. There is a limit to how heavy a neutron star can get before it collapses. Push enough mass into a neutron star and the internal pressure can no longer hold it up. Gravity wins. The star collapses completely, and a black hole forms. Theorists have been calculating where that boundary sits for decades, and the answer depends on understanding the behavior of matter under pressures so extreme that no laboratory on Earth can replicate them. The theoretical upper limit is somewhere between roughly 2 and 3 times the mass of our Sun. In 2020, astronomers announced the detection of a neutron star with a mass of approximately 2.17 times the mass of the Sun. The object, called MSPJ 0740-6620, sits just below or near the upper theoretical limit, depending on which equation of state for ultra-dense matter the calculation uses. The measurement came from combining data from 2 separate telescopes, the Green Bank Telescope in West Virginia and the NICA instrument aboard the International Space Station. The detection matters because the interior of a neutron star at these masses is completely unknown territory. Models of neutron star interiors propose different states of matter at the core. Standard nuclear matter, meaning densely packed neutrons, is one possibility. Strange quark matter, where the normal neutron structure breaks down into its constituent quarks, is another. Some models propose the existence of exotic particles called hyperons, appearing under sufficient pressure. Each of these possibilities predicts a slightly different maximum mass. Finding a neutron star near the limit helps eliminate some models and constrain others. A neutron star at the boundary is also interesting for what it has not yet done. Something is holding it up. The internal pressure from quantum effects, called degeneracy pressure, is resisting gravity at a level that a black hole could not. The object exists in a regime where the physics of matter is pushed to its absolute limits and somehow remains stable. Study it closely enough, and it teaches us what matter can do at conditions no other object in the universe provides access to. The NICER instrument has produced detailed maps of hotspots on neutron star surfaces, tracking how X-ray emissions pulse as the star rotates. From those maps, scientists calculate the star's mass and radius simultaneously. The combination tightly constrains the internal physics. Each measurement chips away at the range of possible interior states. But neutron stars, extreme as they are, exist in a clear category. They are known objects with known physics, even if that physics is at the edge of understanding. What is harder to explain are the black holes found in mass ranges that current stellar evolution theory struggles to produce. Between the heaviest neutron stars and the lightest confirmed black holes sits a gap. For years it was empty. Then, instruments started finding things in it. Stellar black holes form when massive stars die. The collapsed core, too heavy for neutron star pressure to support, continues collapsing through its own horizon. These black holes range from roughly 5 to a few tens of times the mass of the Sun. At the other extreme, supermassive black holes sit at the centers of galaxies and range from millions to tens of billions of solar masses. They formed through a combination of early universe conditions, mergers, and billions of years of mass accumulation. Between those two categories sits a mass range where almost nothing was confirmed to exist. Black holes between roughly 100 and 100,000 solar masses. Intermediate mass black holes. Theorists predicted they should exist as a bridge between stellar and supermassive, possibly as the seeds from which supermassive black holes grew. For decades, confirmed detections were nearly absent. The gravitational wave era changed that. In 2020, the LIGO and Virgo gravitational wave detectors picked up a signal designated GW190521. Analysis showed it was produced by the merger of two black holes, one of approximately 66 solar masses and one of roughly 85 solar masses. The merger produced a final black hole of approximately 142 solar masses. That final object sits squarely in the intermediate mass range. It also sits in what physicists call the pair instability gap. Black holes between roughly 60 and 130 solar masses are theoretically hard to produce from a single stellar collapse, because stars in that mass range undergo particular instability during their final stages that causes them to partially or completely blow themselves apart, rather than collapsing cleanly. The GW190521 event produced not one but two black holes in or near this gap, raising the immediate question of how they formed. One candidate is that they were themselves the products of earlier black hole mergers, second-generation objects that grew through collisions rather than stellar collapse. If true, it implies dense environments where black hole mergers are common, and multiple generations of mergers can occur within a cosmologically short time. The leading candidate environment is the dense stellar region around a supermassive black hole's accretion disk. A separate class of detections has since added more intermediate mass candidates. Some are identified through their gravitational effects on surrounding stars in dense globular clusters. Others appear as unusual X-ray sources where gas falling toward the object shows temperature and luminosity patterns more consistent with an intermediate mass object than a stellar one. The missing link between stellar black holes and the giants at galactic centers is filling in. The bridge is real, and the giant at the center of our own galaxy has a history far more violent than it appears today. At the center of the Milky Way, roughly 26,000 light-years from Earth, sits a black hole 4 million times the mass of our Sun. Astronomers designated it Sagittarius A star. For most of the time humanity has existed, this object appeared dormant. Its accretion disk, the ring of gas and dust feeding into it, is thin and dim compared to the blazing active galactic nuclei seen in distant galaxies. Compared to the most powerful quasars, where supermassive black holes are consuming matter at rates that outshine entire galaxies, Sagittarius A star is nearly silent. Nearly. The evidence for a violent past began accumulating in the 2000s. A team studying X-ray emission from gas clouds in the central regions of the galaxy found something puzzling. The clouds were glowing in X-rays, in patterns that indicated they had been illuminated by a powerful X-ray source. When the team calculated what could have produced the illumination, the source had to have been roughly 1 million times brighter than Sagittarius A star is today. And the timing of the illumination, worked out from the light travel time across the distances involved, pointed to an event somewhere between 2 million and 6 million years ago. 2 million to 6 million years ago, the hominid ancestors of humanity were walking across the African savanna. The black hole at the center of our galaxy was erupting. In 2013, the Hubble Space Telescope imaged a vast cone-shaped structure of ionized gas extending from the galactic center up through the halo of the Milky Way and piercing the Magellanic Stream. A ribbon of gas trailing our two nearest neighboring galaxies at a distance of roughly 200,000 light-years. The cone's geometry points back directly to Sagittarius A star. The ionization was produced by a flood of ultraviolet radiation from the black hole's active phase. The Milky Way is currently a quiet galaxy. Its central black hole sits in what astronomers call a low luminosity state, but the evidence of its active period is scattered across the galaxy and beyond in the form of ionized gas, heated clouds, and enormous structures visible in X-ray and gamma-ray light. Those structures, extending above and below the galactic plane, were detected a decade earlier by a different instrument, and they carried their own mystery. In 2010, astronomers analyzing data from the Fermi Gamma-ray Space Telescope found two enormous structures extending from the center of the Milky Way, one stretching upward above the galactic plane, one stretching downward below it, each one extending roughly 25,000 light-years in length. Together they form a figure 8 shape centered precisely on Sagittarius A star, filling a volume far larger than the visible disk of our galaxy. These are the Fermi Bubbles, confirmed by multiple instruments and multiple independent teams. The structures glow in gamma rays and X-rays. Their edges are sharp, which in astrophysics indicates a shock front, a boundary where fast-moving material has slammed into slower surrounding gas. The sharpness implies the structures formed in a relatively short and intense event, rather than a slow, ongoing process. The leading explanation connects directly to Sagittarius A star's active period, a powerful outflow from the central black hole during its active phase, carrying enormous energy, pushed material above and below the galactic plane. As that material traveled outward, it swept up the surrounding gas like a snowplow and compressed it into the sharp bubble edges visible today. The process is called an active galactic nucleus outflow, and similar structures appear around other galaxies with active central black holes. The energy required to create the Fermi bubbles is enormous. Estimates put it at roughly 100 times what the most powerful supernova explosions release. Some researchers have proposed an alternative origin, not the black hole, but a burst of rapid star formation in the galactic center, releasing massive stellar winds and supernova explosions all at once. A starburst explanation. Both mechanisms could contribute. The debate over the primary energy source is ongoing. What is settled is the physical reality of the structures, their size, their energy content, and their origin in the galactic center. Then, in 2020, a team reanalyzing the data found something else. Inside the Fermi Bubbles, nested within them, a separate structure appeared, narrower, hotter, and with sharper edges than the outer bubbles. Dubbed the Aerosita bubbles by some researchers and microwave haze by others, this inner structure appears to trace a more recent or more energetic phase of the same general outflow process. The outer bubbles and the inner structure may represent different episodes of activity, different pulses of energy from the galactic center, separated by time. The Milky Way has layers of its own violent history written in structures above and below the plane where the stars orbit quietly. Each layer represents an event. Each event involved energies that dwarf anything human civilization has ever imagined. And the outflows from Sagittarius A star are modest compared to what happens when you zoom out to structures spanning not thousands, but billions of light years. Because on the largest scales of all, the universe is hiding structures so enormous they should be physically impossible. In 2021, astronomers mapping the positions of galaxies across a wide section of the sky found something that stopped the analysis cold. A curved arrangement of galaxies stretching across 1.3 billion light-years in a single, coherent arc. They named it the Giant Arc. It sits at a distance of roughly 9.2 billion light-years from Earth, meaning the light we observe left it when the universe was less than half its current age. The structure is enormous enough that if you could see it with the naked eye, it would span roughly 1/5 of the observable sky. The problem is that it should not be there. Cosmology operates under a foundational assumption called the cosmological principle. The universe, on large enough scales, is uniform. Matter is spread roughly evenly in every direction. Structures exist, galaxies, clusters, filaments, but above a certain scale, roughly 300 million light-years, the distribution smooths out. No single structure should dominate. The universe should look the same in every direction once you zoom out far enough. 1.3 billion light-years is more than 4 times that limit. The Giant Arc is not alone in challenging this assumption. Before it, astronomers had already found the Hercules Corona Borealis Great Wall, a structure discovered through the distribution of gamma-ray bursts and estimated at roughly 10 billion light-years in length. A second structure, called the Giant Gamma-Ray Burst Ring, spans roughly 5 billion light-years. Each individual discovery attracted debate about methodology and interpretation. Together they form a pattern of anomalies that cosmologists cannot easily set aside. The Giant Arc's discoverer, an astronomer named Alexia Lopez, calculated the probability of such a structure forming under the standard cosmological model at less than 1 in 50,000. That is a statistical signal serious enough that several teams immediately began working to verify or challenge the finding. Some researchers proposed that the arc is not a single physical structure, but a chance alignment of unconnected galaxy clusters along the line of sight. The visual appearance of a connected arc being produced by projection of separately distributed objects onto the sky. This is a legitimate possibility and has not been ruled out. Others took the observation at face value and pointed to what it implies. If the Giant Arc is real, as a coherent structure, the cosmological principle needs revision. The universe has preferred arrangements, preferred scales of organization that current models do not account for. Something in the universe's formation history, perhaps some early pattern in the distribution of matter before the first galaxies formed, may be imprinting structures far larger than any simulation has produced. A revision to the cosmological principle would cascade through cosmology. Every calculation that assumes uniformity would need re-examination. The standard model's predictions for how structures grow and cluster over time would need adjustment. The tools used to interpret the cosmic microwave background, gravitational lensing maps, and galaxy surveys all carry the flatness and uniformity assumptions somewhere in their foundations. The giant arc observation has been submitted for peer review, published, and is undergoing ongoing scrutiny. It is real as a detected signal. Its interpretation remains contested. And if 1.3 billion light-years sounds extreme, the largest known structure in the observable universe is almost 8 times larger. It was found by following the most violent explosions in the universe, and its size creates a problem that has never been resolved. Gamma-ray bursts are the most energetic explosions in the observable universe. When a massive star collapses into a black hole, or when 2 neutron stars spiral together and merge, the resulting explosion can briefly outshine every galaxy in the observable universe combined. The burst of gamma rays that follows travels across billions of light-years and arrives at Earth with enough energy to register clearly on orbiting detectors. Gamma-ray bursts are so bright that astronomers use them as beacons to map the distant universe, because wherever a burst fires, it marks the location of a galaxy. In 2013, a team analyzed the positions of gamma-ray bursts detected over several years and found a clustering that defied expectation. In one region of the sky, bursts were appearing far more often than the background rate. When the team mapped the positions of these bursts in 3 dimensions, accounting for their distances, they traced out a ring-shaped structure roughly 5 billion light-years across. 5 billion light-years, confirmed by gamma-ray burst data from multiple sources. The structure is called the Hercules Corona Borealis Great Wall by some researchers, and the Giant Ring by others. At that scale, it is not just the largest structure ever found. It is a structure so large that light takes 10 billion years to cross it from one end to the other. 10 billion years. The universe itself is only 13.8 billion years old. Under the cosmological principle, structures of this scale are physically prohibited. The universe has not existed long enough for gravity to gather matter across 10 billion light-years into a coherent arrangement. Gravity travels at the speed of light. For matter on opposite ends of a 10 billion light-year structure to have influenced each other gravitationally, light would have needed to travel between them, which takes 10 billion years. The universe is barely older than that. There has been almost no time for gravity to organize matter on this scale into anything coherent. And yet, the clustering appears. The debate around this structure centers partly on whether gamma-ray bursts are reliable tracers of underlying large-scale structure. They require a galaxy to form, and galaxies trace matter distribution. So in principle, the logic is sound. Critics have pointed to possible selection effects, ways in which the observational strategy could artificially produce apparent clustering. The original team addressed several of these concerns in follow-up papers. The debate has not fully closed. If the structure is real as a physical arrangement of matter, cosmology has a serious problem. The standard model produces no mechanism capable of organizing matter on this scale in the available time. Something either happened in the very early universe to prearrange matter before the standard formation processes began, or the universe is fundamentally less uniform than the cosmological principle states. Both possibilities require additions or corrections to the standard model. The scale of those corrections is unknown. When you find something that breaks the rule that the universe looks the same in every direction, the natural next question is whether the universe also rotates the same in every direction. And a study published in 2020 raised the possibility that it might not. Galaxies rotate. That is expected. The angular momentum accumulated during their formation drives stars in long, curved orbits around the galactic center. What is not expected is for galaxies across enormous distances to show a coordinated preference in the direction they rotate. In 2020, a team of researchers analyzed the rotation directions of about 14,000 galaxies observed by the Sloan Digital Sky Survey. Spiral galaxies have a visible handedness. arms curling clockwise or counterclockwise when viewed from a given direction. In a truly uniform isotropic universe, these should be randomly distributed, half clockwise, half counterclockwise, with no preference in any direction. The team found a statistically significant asymmetry in one particular region of the sky. Galaxies with one rotation direction outnumbered galaxies rotating the other way by a margin large enough to be unlikely by chance. The signal was not dramatic in absolute terms, but was consistent across different statistical tests applied to the same dataset. If confirmed, this asymmetry implies that the universe has a preferred axis, an orientation in space that is different from other orientations. Cosmologists call this a violation of isotropy. Isotropy is the assumption that the universe looks identical in all directions when averaged over large scales. It is a foundational assumption sitting directly beneath the cosmological principle, beneath the standard model of cosmology, beneath every large-scale calculation done in the field. An axis of rotation for the universe would mean that the universe itself was born with some angular momentum, some spin, imprinted from conditions at or before the Big Bang. It would mean that the geometry of space is not perfectly symmetrical. It would also predict that other observations, the cosmic microwave background, the distribution of quasars, the large-scale filaments of the cosmic web, might show subtle directional preferences when examined with sufficient precision. Some previous analyses had hinted at similar effects. A controversial result from Planck cosmic microwave background data showed a slight alignment of certain large-scale temperature patterns along a specific direction, sometimes called the axis of evil in the literature. That label reflects the irritation it caused, and an anisotropy at the largest scales is exactly the kind of thing the standard model predicts should not appear. Independent confirmation of the galaxy rotation asymmetry has been mixed. Some subsequent studies found similar signals. Others found no significant deviation from randomness in separate datasets. The question is open. A universe that spins is philosophically and physically different from a universe that does not. Spin has a direction. A direction implies a geometry. A geometry at cosmological scales would rewrite the equations governing cosmic expansion, structure formation, and potentially the nature of dark energy itself. In the spaces between all this large-scale structure, between the filaments and clusters and arcs and spinning galaxies, are the voids, the vast empty regions that make up most of the universe's volume. They look empty. They are not. Zoom out far enough from any galaxy cluster, and you eventually reach a region where almost nothing exists. Cosmic voids are underdense regions of space, bubbles in the cosmic web where matter is sparse compared to the filaments and sheets surrounding them. They range in size from a few tens of millions of light-years to several 100 million light-years across. The largest confirmed void, the KBC void, may extend roughly 2 billion light-years in diameter, and our own Milky Way sits near its center. Voids are not empty in the absolute sense. They contain galaxies, gas, and dark matter, just far less of all of it than the surrounding structure. The galaxy density inside a typical void is roughly 20% of the cosmic average. Gravity has been draining matter from void interiors for billions of years, pulling it outward toward the surrounding filaments and cluster walls. Voids grow over time, expanding as matter leaves them, and the surrounding walls become denser. This growth has a measurable effect on the cosmic microwave background. Photons traveling through a void gain a tiny amount of energy as they enter, because the gravitational potential is shallower than average. They lose an amount of energy as they exit, for the same reason. In a static universe, these effects would cancel. In an expanding universe dominated by dark energy, the void expands while the photon is crossing it, changing the gravitational potential mid-journey and leaving a faint temperature imprint on the background radiation. This imprint, called the integrated Sachs-Wolf effect, has been detected. It is direct observational evidence of dark energy's effect on photon travel through large-scale structure. The cold spot discussed earlier sits in the direction of a large void. The connection between voids and cosmic microwave background anomalies is an active research area. At the edges of voids, the story changes. Where voids meet the surrounding filaments and sheets, matter piles up in long walls and cluster chains. These boundaries are among the densest regions of the cosmic web. Galaxies near void edges show different properties than galaxies in clusters. They tend to be bluer, more actively star-forming, and less massive. The low-density void environment allows star formation to proceed without the disruptive effects of neighboring galaxies, while the filament environment provides fresh gas to fuel it. Some researchers have proposed that void interiors are also important testing grounds for dark energy and modified gravity theories. Because voids are underdense, the gravitational forces inside them are weaker than average. This makes them sensitive probes of how gravity behaves in low-density environments. If dark energy or modifications to gravity produce effects that are density-dependent, voids would show those effects more clearly than dense cluster environments. The KBC void, if real at the scale some measurements suggest, could contribute to the Hubble tension. A galaxy sitting inside an underdense region would measure a slightly faster local expansion rate than the cosmic average, because the surrounding dense walls are pulling matter away from the void center. This local boost in expansion could explain part of the discrepancy between the local and early universe measurements of the Hubble constant. Voids are the universe's empty rooms. And empty rooms, it turns out, contain a great deal of physics. The universe is filled with these layers of structure, and all of it, the filaments, the clusters, the voids, the arcs, the bubbles, is moving toward one end. Scientists have now built a picture of what that end looks like, and it is strange in a way that goes beyond dramatic. The universe will not end with a bang. Based on current observational data, the most supported model for the universe's fate is called the Big Freeze, sometimes referred to as heat death. It is a long, slow process, measured in timescales so vast they make the current age of the universe look like a single breath. The mechanism is straightforward. The second law of thermodynamics states that the total entropy of a closed system increases over time. The universe trends towards maximum disorder, where energy is spread so evenly that no useful work can be done. Temperature differences disappear, motion stops, light fades. Here is the sequence as current physics describes it. Stars will continue forming for roughly 100 trillion years as gas slowly collapses under gravity. By 100 trillion years from now, the last red dwarf stars will exhaust their fuel and cool to dark cinders. No new stars will ignite. The galaxies will go dark, filled with stellar remnants, white dwarfs, neutron stars, black holes, and cold planetary bodies drifting through the dark. Over the next several quadrillion years, white dwarfs will slowly radiate their remaining heat and cool to black dwarfs. No confirmed black dwarf exists yet, because the universe is not old enough for any white dwarf to have cooled that far. Every black dwarf that will ever exist is currently a white dwarf, still glowing faintly. Beyond that, proton decay becomes relevant. The standard model of particle physics does not include proton decay, but extensions of the theory predict that protons are not perfectly stable. Given enough time, on the order of 10 to the power of 40 years or beyond, protons decay into lighter particles. If proton decay occurs, ordinary matter dissolves. White dwarfs and neutron stars evaporate particle by particle over timescales the mind cannot hold. Black holes outlast all of this. Through a process Hawking described theoretically in 1974, Black holes emit radiation by a quantum mechanical effect at their event horizon. This Hawking radiation causes black holes to very slowly lose mass over time. A stellar mass black hole takes roughly 10 to the power of 67 years to fully evaporate. A supermassive black hole with billions of solar masses takes closer to 10 to the power of 100 years. After complete evaporation, space is left with only the lowest energy photons and particles, spreading outward across an ever-expanding universe. Eventually, the expansion driven by dark energy dilutes even that. The final state is a universe of extraordinary near emptiness, cooling toward absolute zero, where the remaining photons are so stretched by expansion they carry almost no energy. This is the big freeze. This fate is not guaranteed. It depends on dark energy remaining constant. If dark energy grows stronger over time, a different scenario unfolds. The Big Rip, where accelerating expansion eventually overcomes all forces, including the electromagnetic bonds holding atoms together. If dark energy weakens and reverses, a big crunch brings everything back together. Current data favors the freeze, but the 2024 results from the Dark Energy Spectroscopic Instrument, hinting at evolving dark energy, leave the question genuinely open. The universe has a life cycle, and embedded within it is a problem that Hawking spent decades trying to solve. A paradox about what happens to information that falls into a black hole, and what its answer means for reality itself. Stephen Hawking spent much of the last decades of his life wrestling with a problem he helped create. When he calculated in 1974 that black holes emit thermal radiation and slowly evaporate, he did not initially realize the depth of the problem embedded in that calculation. The radiation is thermal, meaning it is essentially random. It carries no information about what fell into the black hole to create it. By the time the black hole has fully evaporated, the radiation it emitted is featureless heat. The original matter, the stars, gas, planets, perhaps entire civilizations in principle, that fell in is gone, and the radiation replacing it carries no record of what that matter was. This violates one of the deepest principles in quantum mechanics. Quantum mechanics requires that information is conserved. The complete description of any physical state can always, in principle, be recovered. Physical processes are reversible at the fundamental level. You can run the equations forward or backward, and the information is preserved. A black hole that destroys information when it evaporates makes quantum mechanics and general relativity fundamentally incompatible, and one of them must be wrong or incomplete. This is the black hole information paradox, confirmed as a genuine problem, unresolved in its complete form for 50 years. Hawking's original position was that information is genuinely lost. He later changed his view. In 2004, he publicly conceded that information is probably preserved, though he did not have a complete mechanism to explain how. The concession came after decades of theoretical work suggesting that the information must escape somehow, even if the details were unclear. The leading framework for how information escapes is holography. The holographic principle, developed through the work of multiple theorists in the 1990s, proposes that the information content of any volume of space is fully encoded on the boundary surface surrounding it. Applied to black holes, this means all information about what fell in is somehow encoded on the event horizon surface. As the black hole evaporates and the horizon shrinks, that information is gradually released into the Hawking radiation in an extremely scrambled but technically recoverable form. A major partial step toward resolving the paradox appeared in 2019, when several teams published calculations using a technique combining elements of quantum gravity. Their calculations showed that the entropy of Hawking radiation follows a curve consistent with information preservation rather than information loss, at least in certain theoretical settings. This was celebrated as a significant advance. However, the calculation was performed in simplified theoretical models, not in the full complexity of our actual universe. The complete resolution of the information paradox requires a theory that unifies quantum mechanics and gravity, which remains the central unsolved problem in theoretical physics. The 2019 result suggests the answer is achievable within that framework. The framework itself does not yet exist in its complete form. A black hole that preserves information while appearing to destroy it is doing something deeply strange at its horizon. Understanding that strangeness may be the key to unlocking physics beyond everything we currently know. And over the past decade, the accumulation of results from Webb, from gravitational wave detectors, from cosmic microwave background surveys, all points in the same direction. The physics we have is not enough. What comes next is the hunt for what replaces it. Everything discovered in the past decade shares a common thread. Galaxies too old for the timeline, structures too large for the uniformity principle, an expansion rate that refuses to converge, a signal from dark matter that keeps appearing and disappearing in the data, Fermi bubbles above and below our galaxy, recording a violent past, rotating filaments of the cosmic web, a cold spot 1 billion light-years wide that the best explanation accounts for only partially, a universe that may spin. Each discovery, taken alone, could be a measurement error, a local anomaly, a limitation of current instruments. Taken together, they form a consistent pattern. The standard model of cosmology, built over decades and supported by overwhelming evidence, is incomplete. Something is missing from the picture. Several somethings, possibly. This is confirmed in the sense that the physics community broadly acknowledges the tensions are real. The Hubble tension is not going away. The large-scale structure anomalies are accumulating. The nature of dark matter and dark energy remain open. The information paradox is unsolved. These are among the most prominent open problems in all of science, not on the fringes, but at the center of the field's attention. What humanity does next depends on tools either recently deployed or currently under construction. The Vera C. Rubin Observatory in Chile, scheduled to begin full science operations in 2025, will survey the entire southern sky repeatedly over 10 years, cataloging billions of galaxies and detecting transient events like supernovae and variable stars at a rate no previous telescope approached. Its dataset will allow the most precise measurements of large-scale structure ever attempted, directly testing whether the giant arc and similar anomalies represent real structure or observational artifacts. It will also provide the most detailed weak gravitational lensing maps ever made, which trace the distribution of dark matter across cosmic scales with unprecedented precision. The Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will conduct wide-field infrared surveys complementing Webb's deep pointings, where Webb stares narrow and deep, Roman scans wide. Together, they cover a range of cosmic territory that neither could address alone. Roman is specifically designed to measure dark energy's behavior over cosmic time, producing datasets that will either confirm the hints of dark energy evolution seen in 2024 or rule them out. The Square Kilometre Array, a radio telescope network being built across South Africa and Australia, will eventually become the most sensitive radio observatory ever constructed. Its sensitivity to fast radio bursts will locate sources precisely enough to identify host galaxies for almost every detected burst, solving the source identification problem that currently leaves most bursts unexplained. It will also map the distribution of hydrogen gas across vast regions of the universe, providing an independent tracer of large-scale structure. On the gravitational wavefront, the Laser Interferometer Space Antenna, a space-based gravitational wave detector planned for the early 2030s, will detect mergers of supermassive black holes across the observable universe. the most powerful gravitational wave sources possible. Each detection will carry information about the host galaxy, the mass history of the merging black holes, and the expansion rate of the universe at the time of the merger. It will also probe the physics of extreme space-time curvature in ways ground-based detectors cannot reach. Physics beyond the standard model is not a hope, it is a prediction. The data demands it. The only question is which direction the new physics lies and which instrument finds the first unambiguous signal pointing that way. The universe is not finished revealing itself. Every answer pulled from the dark opens 3 more questions. Every instrument built to close a gap finds something unexpected sitting in the gap beside the answer. This has been true since Galileo pointed the first telescope at Jupiter and found moons orbiting something other than Earth, overturning centuries of assumption in a single night of observation. Webb found galaxies that broke the timeline. Whatever breaks the model next may already be in a data set, waiting for someone to look in the right direction. The universe is vast, strange, and still largely unknown, and it is actively telling us so. For nearly a century, one assumption has held the entire structure of cosmology together. The cosmological principle states that the universe, viewed at large enough scales, is the same everywhere and in every direction. No special locations, no preferred orientations, matter distributed uniformly when you zoom out far enough. This principle is not just a philosophical preference. It is a mathematical requirement baked into Einstein's equations as applied to the universe as a whole. Remove it, and the equations become enormously more complicated. Models of cosmic expansion, galaxy formation, and dark energy behavior all depend on it at their foundations. The giant arc, the Hercules Corona Borealis Great Wall, the galaxy rotation asymmetry, and the cold spot are each individually contested. Together, they apply pressure on the cosmological principle from multiple independent directions simultaneously. And in 2022, a study using quasars pushed that pressure further. Quasars are the extremely luminous cores of distant galaxies powered by actively feeding supermassive black holes. They are among the brightest objects in the observable universe and can be detected across tens of billions of light years. A team analyzed the distribution of roughly 1 million quasars mapped by the Wide Field Infrared Survey Explorer satellite and found a statistically significant dipole pattern. A dipole means more quasars appear concentrated in one direction of the sky than the opposite direction. A dipole in the quasar distribution was expected. Earth moves through space, and that motion produces a slight apparent concentration of sources in the direction of travel. The team measured the dipole, compared it to the known motion of Earth, and found the quasar dipole was significantly larger than the motion alone could explain. The excess pointed to a large-scale asymmetry in the universe's structure itself, not just Earth's local motion through it. The result was published in a peer-reviewed journal and has since been followed by independent analyses with similar conclusions. The discrepancy between the expected and observed dipole is large enough that some researchers describe it as a genuine crisis for isotropy. Crisis is a strong word in science. It means the tension between observation and theory has reached a level where the theory requires modification rather than minor adjustment. The standard cosmological model has faced crises before and survived them through extensions and refinements rather than wholesale replacement. The Hubble Tension reached crisis status by most definitions. The isotropy challenge is now approaching it. What makes the quasar result particularly difficult to dismiss is its independence from the other anomalies. The giant arc was found through optical galaxy surveys. The rotation asymmetry came from spiral galaxy observations. The quasar dipole comes from infrared observations of a completely different class of objects at greater distances. 3 independent datasets, 3 independent object types, 3 independent instrument systems. all pointing toward large-scale structure that does not match the standard expectation. A cosmological principle that fails at the largest scales does not necessarily mean a cosmological principle that fails everywhere. The universe may be uniform at scales just beyond what current surveys can map, and the anomalies may represent a transition scale rather than a fundamental breakdown. This is scientifically testable. Surveys covering larger volumes with greater sensitivity will either find the universe smoothing out at greater distances, confirming the principle at a revised scale, or they will find the anomalies extending further, requiring a deeper revision. The Vera C. Rubin Observatory and the Square Kilometre Array will map enough of the universe to test this directly. The answer will arrive within roughly a decade. What was once cosmology's most secure assumption is now one of its most actively tested claims. And if the principle fails, the models built on top of it face revision at every level. Even the question of what the universe looks like from the outside, its overall shape and topology, may need to be reopened. Most people picture the universe as a vast, flat expanse stretching outward in all directions without limit. The Standard Model supports this picture. Measurements of the cosmic microwave background have consistently found the universe's spatial curvature to be indistinguishably close to zero, meaning space is flat to within the precision of current instruments. Flat geometry does not mean the universe is infinite. A flat universe can be finite if it has a topology that wraps around on itself, like the surface of a cylinder or a more complex three-dimensional equivalent. In such a universe, traveling far enough in one direction would eventually bring you back to your starting point. The universe would have a finite size but no edge. This is not wild speculation. It is a testable prediction with a specific observational signature. In a universe small enough for light to have traveled across it since the Big Bang, objects near the boundary should appear in multiple locations in the sky simultaneously. A specific pattern of repeated circles in the cosmic microwave background, matching precisely in temperature pattern, would appear wherever the topology causes our observable sphere to intersect itself. Teams have searched the Planck satellite data for these matching circles and found no confirmed signal. The absence of matching circles sets a lower limit on the universe's size. If it wraps around, it does so on a scale larger than our current observational horizon. The observable universe, the region from which light has had time to reach us since the Big Bang, spans roughly 93 billion light-years in diameter. The full universe, if finite, is at least this large and probably much larger. The 2019 paper suggesting positive curvature introduced a different geometric possibility. A positively curved universe shaped like a three-dimensional sphere, the higher dimensional equivalent of a ball's surface, is both finite and without edges. Travel far enough and you return home. On this geometry, the apparent cosmic microwave background anomalies, including the suppression of large-scale temperature fluctuations, fit more naturally than on a flat geometry. The debate between flat and curved cuts directly to the Hubble tension. A positively curved universe measurements. Some analyses show the curvature correction brings the early universe Hubble constant closer to the local measurement. Solving two major problems with one geometric correction is attractive, but physics has been burned before by elegant solutions that turned out to be coincidences. What makes the shape question more urgent than it might appear is its connection to questions about what exists beyond the observable horizon. If the universe is flat and infinite, then regions beyond our horizon are essentially identical to what we can observe. The physics there is the same. If the universe is finite and curved, the topology beyond our horizon is constrained. If the universe has a specific topology that wraps around, then the region we call our universe is genuinely all there is. No infinite multiverse of separate patches, just our finite, closed cosmos. The shape of the universe determines whether the multiverse is a physical necessity or merely a theoretical option. That alone makes it one of the most consequential open questions in all of science. Within our observable universe, as the larger questions remain open, instruments are picking up signals from objects behaving in ways that push the boundaries of known physics. And the strangest of those signals may be arriving from neutron stars doing something no theory fully anticipated. In 2017, two neutron stars, 130 million light-years away, completed a spiral that had been tightening for over 1 billion years. They merged. The collision released more energy in roughly 1 second than our Sun will emit across its entire 10 billion-year lifetime. Gravitational wave detectors in the United States and Europe caught the ripple in space-time as it arrived. Simultaneously, space telescopes detected a burst of gamma rays arriving from the same direction less than 2 seconds later. And over the following days, ground-based observatories watched the aftermath glow across multiple wavelengths as it slowly faded. This event, designated GW170817, was the first confirmed detection of a neutron star merger in both gravitational waves and light simultaneously. It answered questions that had been open for decades. The gamma-ray burst confirmed that at least some short gamma-ray bursts, the quick flashes lasting under 2 seconds, come from neutron star mergers. This had been theorized for years. One observation proved it. The kilonova, the glowing cloud of ejected material, showed spectroscopic signatures of heavy elements: gold, platinum, uranium, and dozens of others. The nuclear physics process responsible, called the rapid neutron capture process, had been theorized to occur in environments with extreme neutron densities. A neutron star merger provides exactly that environment. The confirmation carries a profound implication. Every gold atom on Earth, in every piece of jewelry, every circuit board, every coin was forged in the collision of two dead stars somewhere in the history of the galaxy. The merger of two neutron stars is the factory for heavy elements. The Big Bang produced hydrogen and helium. Population 3 stars produced the first carbon and oxygen. Supernovae spread iron and elements up to a certain atomic weight. Neutron star mergers filled in everything heavier. The gravitational wave signal from GW170817 also provided an independent measurement of the Hubble constant. The precise shape of the gravitational wave signal encodes the distance to the merger, and the redshift of the host galaxy gives the recession velocity. Combining them yields the expansion rate without any of the calibration ladders used in traditional measurements. The value obtained sits between the two competing measurements of the Hubble constant, which is either a hint toward a resolution or a reminder that the measurement needs more events to reach precision. Since 2017, more neutron star mergers have been detected through gravitational waves. Each one adds constraints on neutron star physics, heavy element production rates, and the Hubble constant. The data set is growing. But the merger that shook the physics community also raised a question about what happens when the merged object is not quite heavy enough to immediately collapse into a black hole. For a brief period after the collision, simulations suggest a hypermassive neutron star may form, spinning rapidly, radiating gravitational waves at frequencies higher than current detectors can fully resolve. The signal from that brief object, lasting perhaps milliseconds before collapse, carries information about the equation of state of ultra-dense matter that no other observation can provide. Next-generation gravitational wave detectors are being designed specifically to catch that signal. The universe speaks in many frequencies, and some of the strangest messages arrive not from collisions, but from the slow, patient work of gravity acting on matter over billions of years in places far from any star. The outer edges of galaxies should slow down. This is basic orbital mechanics. Planets further from the Sun move more slowly because the Sun's gravitational pull weakens with distance. The same logic applies to stars orbiting a galaxy's center. Stars near the center orbit quickly, Stars further out should orbit more slowly as the gravitational influence of the concentrated central mass weakens. They do not. When astronomer Vera Rubin measured the rotation speeds of stars in spiral galaxies in the 1960s and 70s, she found something that contradicted the prediction completely. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center. The rotation curves, as they are called, were flat where they should have dropped off. The outer stars were moving faster than the visible mass of the galaxy could gravitationally support. Rubin's finding was initially met with skepticism. It was eventually confirmed across hundreds of galaxies by multiple independent teams. The flat rotation curves are real. They are one of the strongest pieces of evidence for dark matter. The only explanation consistent with the data is that galaxies are embedded in enormous halos of invisible mass, extending far beyond their visible edges. The dark matter halo reaches out roughly 10 times further than the visible disk of stars and gas. Its total mass dwarfs the mass of everything you can see. The Milky Way's dark matter halo, by current estimates, extends roughly 600,000 light-years from the galactic center. The visible disk of the Milky Way spans roughly 100,000 light-years. Everything beyond that visible edge, out to 600,000 light-years, is dominated by a dark matter structure we cannot directly image, only infer from gravitational effects. In the outer halo, conditions are extraordinary in their emptiness. Gas density drops to almost nothing. Star formation essentially stops. The few stars that exist there are ancient, some of the oldest in the galaxy, scattered in a sparse spherical distribution rather than the flat disk that defines the galaxy's visible face. Recent surveys have found unexpected structures in this outer halo, streams of stars stretching for hundreds of thousands of light-years. The tidally disrupted remains of smaller satellite galaxies that passed too close to the Milky Way and were pulled apart by gravitational forces. These streams preserve the orbital history of their parent objects, acting as records of past interactions and mergers that shaped the Milky Way over billions of years. Several of these streams trace the remains of dwarf galaxies that no longer exist as coherent objects, fully dissolved into the Milky Way's halo. By mapping the streams precisely, astronomers can work backward to reconstruct the properties of the original galaxy, its mass, its orbit, its dark matter content. This acts as a forensic tool for understanding what the Milky Way consumed on its way to becoming the galaxy it is today. The Milky Way is still consuming. The Sagittarius dwarf galaxy, a small companion currently passing through our galaxy's outer disk, is being actively disrupted. Its stars are being pulled into a stream visible across the entire sky in certain infrared surveys. At the far edges of the halo, where dark matter density drops and the influence of neighboring galaxies begins, the boundary between our galaxy and intergalactic space dissolves into a gradient rather than a clear line. And in intergalactic space itself, an almost unimaginable emptiness interrupted only by the faintest threads of gas connecting one galaxy to another. There are signals arriving from sources that have no satisfying explanation. The night sky between the stars and galaxies should be dark. It is not completely dark. Astronomers measuring the total brightness of the sky in ultraviolet and optical wavelengths have consistently found more light than can be accounted for by adding up every known source. Every star, every galaxy, every quasar within observational range is catalogued. The light from all of them is calculated. The measured background exceeds that total. This excess is called the cosmic optical background, and it has been a subject of debate for years. Some researchers attributed it to faint, unresolved sources, too dim to be individually detected, but collectively contributing light, dwarf galaxies, intracluster stars stripped from their host galaxies, or extremely distant objects below the detection threshold of current surveys. In 2021, a team used data from the New Horizons spacecraft which had traveled far enough from the sun that the scattered light from solar dust, a persistent source of contamination for telescopes in the inner solar system, was no longer significant. With that contamination removed, their measurement of the cosmic optical background was cleaner than any previous attempt. The excess remained. In fact, the measurement suggested the excess was roughly twice the light contributed by all known galaxies combined. Twice. Every galaxy we can see is matched by an equal amount of light, with no confirmed source. Several explanations are actively investigated. One proposes that there are far more faint dwarf galaxies than current surveys have detected, scattered throughout the volumes between the bright galaxies we readily observe. Another points to intrahalo light, the glow from stars ejected from galaxies into the space between them during gravitational interactions. A third, more speculative explanation involves the decay of dark matter particles into photons, an extension of the sterile neutrino decay idea discussed earlier. A 2022 study using Hubble Space Telescope data to search for unresolved faint galaxy populations found some contribution from previously uncounted objects, but not enough to close the gap entirely. Webb's sensitivity to faint sources may narrow the mystery further. Its first deep field images revealed galaxies so faint and numerous that astronomers are still working through their implications for the galaxy count. The cosmic optical background excess is confirmed as a real measurement discrepancy. Its source is unknown. The range of proposed explanations spans from the conventional, more galaxies than we can see, to the exotic, dark matter radiating light. Each explanation requires either a previously undetected population of sources or new physics. Both possibilities would change our accounting of what the universe contains. A universe with twice as much light as its visible contents can explain is a universe keeping secrets in its darkest corners. And some of those corners are defined not by what they contain, but by what happened there long ago, in events so energetic they left permanent scars across distances that dwarf anything else in this story. Long gamma-ray bursts are different from the short bursts produced by neutron star mergers. Long bursts last from several seconds to several minutes and release energy equivalent to converting several solar masses entirely into radiation in a single explosion. They come from the death of the most massive stars, those exceeding roughly 20 to 30 times the mass of our Sun, in a specific type of collapse called a collapsar. When the core of such a star collapses directly into a black hole, the outer layers do not simply fall in. They form a rapidly rotating disk around the newborn black hole, and two jets of material are launched perpendicular to that disk at close to the speed of light. Those jets punch through the collapsing star and emerge from both poles. The interaction of the jet with the surrounding material produces the gamma-ray burst. The jet itself continues outward, sweeping up interstellar gas and producing an afterglow visible across the electromagnetic spectrum for days, weeks, sometimes months. The most distant gamma-ray burst ever detected came from roughly 13 billion light-years away, meaning it occurred when the universe was less than 1 billion years old. The progenitor star was a massive population 3 or near population 3 object formed in the early universe. Its death was visible across most of the observable universe. Gamma-ray bursts point their jets in random directions. Earth sits in the crosshairs of these jets purely by chance, and only bursts whose jets happen to point toward us are detectable as gamma-ray bursts. The ones pointing away from us appear as softer X-ray or radio sources, if detected at all. Correcting for this geometric effect, the true rate of long gamma-ray bursts in the observable universe is enormous. The energy in a single long gamma-ray burst jet, if pointed directly at Earth from a distance of a few thousand light-years, would strip away the ozone layer across the hemisphere facing the burst. Extinction-level radiation would follow. At least one mass extinction in Earth's history, the Ordovician event roughly 440 million years ago, has been proposed as a potential gamma-ray burst casualty, though this remains a hypothesis rather than a confirmed cause. The nearest confirmed candidate progenitor for a future long gamma-ray burst within our galaxy is a system called WR104, a Wolf-Rayet star roughly 8,000 light-years away. Whether its jet would point toward Earth when it eventually explodes is unknown. Wolf-Rayet stars are rare and short-lived, and WR104 is expected to explode on an astronomical timescale from now, somewhere between a few thousand and a few 100,000 years. The universe generates events of this magnitude routinely across its history. Every one represents a redistribution of energy on a scale that restructures the surrounding interstellar medium for thousands of light years. The combined effect of all gamma-ray bursts across cosmic history has shaped which regions of galaxies are hospitable to life and which have been repeatedly sterilized by radiation. The galaxy's habitable zones are partly defined by where the gamma-ray bursts were not pointing. We exist in a quiet region of a relatively calm galaxy at a fortunate moment in cosmic history. The universe has been violent enough that our existence required a great deal of cosmic luck, and the more we map that violence, the more we understand just how narrow the conditions for complexity and life actually are, which makes the discovery of what may be the universe's most exotic state of matter, found inside the most extreme objects known, all the more remarkable. Inside a neutron star, under pressures that dwarf anything achievable in any laboratory, something may be happening to matter itself. Ordinary neutrons are made of quarks. 3 quarks bound together by the strong nuclear force give you a neutron. Protons are also 3 quarks, just a different combination. Under normal conditions, quarks are always confined inside hadrons, protons, neutrons, and their relatives. Quarks do not exist freely on their own. The strong force holds them trapped. But squeeze matter hard enough to densities many times greater than ordinary nuclear density, and the boundaries between individual neutrons may dissolve. The quarks from one neutron overlap with the quarks of its neighbor. The concept of a separate neutron loses meaning. You end up with a sea of quarks moving collectively through the star's interior. This state is called quark matter. If quark matter exists inside neutron stars, it changes how those stars respond to disturbances. It changes their maximum mass, their radius, their vibration frequencies, and the gravitational wave signatures they produce during mergers. Gravitational wave observations of neutron star mergers, combined with precise mass and radius measurements from instruments like NICER, are now sensitive enough to constrain what the interior state of matter actually is, at least partially. A further step along this theoretical path leads to strange quark matter. Ordinary quarks come in types: up, down, strange, charm, bottom, and top. Inside a neutron, you have 2 down quarks and 1 up quark. Under extreme pressure, converting some up and down quarks into strange quarks lowers the total energy of the system. A mixture of up, down, and strange quarks, called strange quark matter, may represent a lower energy state than ordinary nuclear matter, meaning it could be the true ground state of matter under extreme conditions. If strange quark matter is the lowest energy state, it is stable. A neutron star with a strange quark matter core would be more stable than one without, and a sufficiently dense piece of strange quark matter encountering ordinary nuclear matter would in theory convert it, nucleon by nucleon, into strange quark matter as well. A tiny, stable nugget of strange quark matter, called a strangelet, contacting ordinary matter would spread through it like a crystallization front, converting everything it touches. This possibility is largely theoretical and the subject of serious safety analyses for particle accelerator experiments. The consensus from those analyses is that strangelet production in accelerators is essentially impossible, and that natural cosmic rays deliver far more energy to Earth's atmosphere than any accelerator produces, without triggering such a conversion. The Earth's existence across billions of years is itself evidence that strange-triggered conversion does not happen spontaneously under conditions present in nature on Earth. In neutron star interiors, however, the conditions are radically different. Whether strange quark matter cores exist in real neutron stars is an open question. Gravitational wave data from GW170817 placed some constraints on neutron star radii that favor relatively stiff equations of state, meaning less exotic interiors, but the constraints allow for quark matter in the densest cores. Future detections of neutron star mergers with next-generation detectors will narrow the range further. Matter itself may have a phase at extreme densities that the universe has been hiding in the interiors of dead stars for billions of years. The universe is not just strange at large scales, it is strange all the way down. In 2023, 5 independent scientific collaborations announced they had found something new, rippling through space-time. Individual gravitational wave events, like the black hole and neutron star mergers detected by LIGO and Virgo, are discrete pulses. They arrive, ring through the detector, and fade. What the 5 collaborations detected was different. A persistent, gentle hum of gravitational waves arriving from all directions simultaneously at frequencies far lower than ground-based detectors can measure. The detection came from pulsar timing arrays. Pulsars are rapidly rotating neutron stars emitting beams of radio waves that sweep across Earth like a cosmic lighthouse with extraordinary regularity. Some pulsars keep time more accurately than atomic clocks. By monitoring dozens of pulsars spread across the galaxy for years, scientists can detect correlated timing shifts across the whole array. Tiny stretches and squeezes in the distances between Earth and the pulsars caused by gravitational waves passing through. The 5 collaborations, operating independently across North America, Europe, China, India, and Australia, each found the same signal. The spatial correlation pattern of the timing variations matched the specific mathematical fingerprint expected from a gravitational wave background. The detection is considered robust. The most likely source is the population of supermassive black hole binaries across the observable universe. When 2 massive galaxies merge, their central supermassive black holes eventually spiral toward each other under gravitational radiation, taking millions or billions of years to complete the process. At any given moment, the universe contains an enormous population of these binaries at various stages of inspiral. Their combined gravitational wave output, summed across all of them across cosmic history, produces exactly the kind of low-frequency hum the pulsar timing arrays detected. The signal's amplitude and spectral shape are consistent with this explanation, though not every detail matches perfectly. Some features of the measured signal are slightly stronger than the standard supermassive black hole binary population predicts. This has opened discussion about possible additional contributors. Cosmic strings, which are theoretical one-dimensional defects in space-time from the early universe, phase transitions in the early universe that released gravitational wave energy, or modifications to the standard black hole merger population. A confirmed detection of cosmic string signals in the gravitational wave background would be extraordinary. Cosmic strings are predicted by certain extensions of particle physics and cosmological inflation models. They are macroscopic defects in space-time, effectively one-dimensional cracks in the fabric of the universe, left over from phase transitions in the very early moments after the Big Bang. A cosmic string vibrating and oscillating over cosmic time emits gravitational waves at a specific spectrum. The current pulsar timing array data cannot fully distinguish between the black hole binary explanation and a cosmic string contribution. The laser interferometer space antenna, operating at different frequencies, will have the sensitivity to distinguish between them. The gravitational wave background means the universe is humming everywhere, Always. Every point in space is being gently squeezed and stretched by the accumulated gravitational waves of 100 billion galaxies worth of black hole mergers, stretching back across cosmic time. We are bathed in gravitational waves from the universe's most violent events, and we have just learned to hear them. The final discovery waiting at the edge of current physics may not come from a new telescope or a new detector. It may come from recognizing what the data already collected is actually telling us, a pattern hiding in plain sight across every observation made in the last decade. Pull back from every discovery in this story and something emerges. Not a single anomaly, not a coincidence, a pattern. The Hubble Tension tells us the universe expanded differently at different points in its history than a single simple model predicts. The galaxy rotation asymmetry tells us the universe may have a preferred direction. The large-scale structures that violate size limits tell us matter organized itself in ways that should not have been possible, given the available time. The cosmic optical background excess tells us there is more light than known sources produce. The fast radio burst, with its 16-day period, tells us something is repeating in a way no known single object should produce. The cold spot tells us the cosmic microwave background has a feature that supervoids only partially explain. Each anomaly has a conventional candidate explanation. Each explanation accounts for part of the signal. None account for all of it, and the anomalies are independent of each other, measured by different instruments, using different methods, targeting different objects at different distances. The pattern they share is a gap, a consistent shortfall between what the standard model predicts and what instruments actually find. That gap appears in the early universe data from Webb. It appears in the large-scale structure surveys. It appears in the cosmic microwave background. It appears in the expansion rate. The gap is not the same size everywhere or in every observation, but it is present, and it is growing clearer as instruments improve. In the history of physics, this kind of pattern has appeared before. In the late 19th century, classical mechanics explained almost everything. Two small anomalies remained: the behavior of light in experiments designed to detect Earth's motion through a hypothetical medium called the aether, and the spectrum of radiation emitted by hot objects. Two gaps, two problems that seemed minor compared to everything physics had successfully explained. Those two gaps required special relativity and quantum mechanics to close. The entire physics of the 20th century came from two small anomalies that refused to go away. The gaps in cosmology today are larger and more numerous than those were. The physics required to close them will almost certainly be more transformative than anything the standard model currently contains. What that physics looks like is genuinely unknown. It may involve new particles that resolve dark matter and modify the expansion history simultaneously. It may involve modifications to gravity that alter how structure forms on large scales. It may involve properties of the early universe's quantum state that imprint preferred directions and scales across the cosmos. It may involve all of these at once. What is known is the direction. Every major telescope project of the next 2 decades is aimed at the gaps. Webb continues staring backward in time, adding to the list of galaxies that break the standard timeline. Rubin Observatory begins systematically mapping structure at the scales where the cosmological principle is being tested. The square-kilometer array will hear radio signals from across the observable universe. The laser interferometer space antenna will feel the gravitational waves of supermassive black hole mergers reaching back to the universe's first billion years. Humanity is building the instruments to hear the universe finish a sentence it started with the Big Bang. The discoveries already in hand are enough to know the sentence is longer and stranger than anyone assumed. Galaxies that should not exist, structures that should not fit, forces that should not dominate, signals that should not repeat. A background hum from the accumulated violence of cosmic history vibrating through every point in space. The universe is vast. It is old beyond any intuitive scale. it is mostly invisible, and it is actively, persistently refusing to be fully understood. That refusal is an invitation. Every anomaly is a door. Behind each one is physics that will change what it means to understand the cosmos. We are standing at the threshold. The next step belongs to whoever looks closer.